And welcome back. Oh, okay, my kettle's really loud now. Um, let's carry on with this problem. So, okay. We're really behind in the days, and if I manage to finish day 10 today, unfortunately, I don't think I can really catch up on the past days 8 and 9 because it's the evening. It's late evening now, and I just don't feel like coding in the late evenings. So tomorrow will be day 11. Maybe we can fully catch up on everything. I don't know. Anyway, let's see if we can manage to finish off 10 today. So I ran this program, which I think is giving the correct answers. But it's been hours now, and it's only up to like 13, so clearly it's too slow. And I'm just going to stop the process there. Let's save this progress, just in case it's of use to us, but clearly we have to write a new algorithm. This doesn't work. So copy that. Stop. We can let the jet engines cool down before we charge them up again. Maybe we could just make a little scratch pad here. Just temp.text. Paste them there. So that's what we've got so far. If we write another algorithm, at least we can compare them with these numbers we got here. Alright. Is my laptop cooling down now? It's been running like this for hours. Problem 14, it seems, is just not doable. Okay, so I did think about it a bit, and I kind of realized something. I almost spelled out a potential solution without realizing it. It just hadn't occurred to me. So I was pointing out this observation that if yeah, let me think for a moment. Oh, I'll get my tea. It's kind of like the coin problem, where you're trying to choose the minimum arrangement of coins to make a number and the coins are different denominations, and that has a dynamic programming solution, but the dynamic programming solution doesn't work here because you can't quite isolate subproblems away from each other like a polynomial number of subproblems, because the reality is the number of subproblems you have is always going to be basically like the order of magnitude will always be something like these numbers multiplied together, because there's no real way around that. With the coin problem, it's different because there's just one total. So it's one number. Alright, but I did say something that was really valuable, and that was the observation that in general, you would like, if you're being greedy, you would like to pick these big buttons first, right? Because they add the most value. You're getting 1, 2, 3, 4, 5, 6, 7, 8 counts every time you press that button. And like your goal is to get this all up, right? So in general, you would press this as much as possible. Now, you could press it the maximum number of times until one of those is full, but that doesn't necessarily mean it's possible to finish after you've done that, so you can't just do that. The greedy algorithm probably doesn't work. I think I can find a counterexample pretty easily, because you then make it so that if there's ties here, you make it so that other buttons will go over the limit or something, I don't know. But, I mean, this observation that you want to go for large things first can be realized by, I mean, basically what we're describing is A-star search, aren't we? Where the heuristic would be number of elements in the button, because that makes the most physical distance to the goal. If we're judging distance by like the Hamming metric or whatever, and we're searching through a search space where the search space is just all nodes with all vectors of this many integers, and the goal is that number, right, that vector right there, and the neighbors are basically each one of these, which node you're taken to from there. So like this gives us a neighbor where you add 1 to 2 and add 1 to 6. And yeah. So maybe A-star search is the way. Because I reckon a lot of the time, even though it's not technically correct to pick the largest buttons as much as possible, then I think in general, if you press the big buttons a lot, you will get to the correct answer, roughly, and you won't have to backtrack much to actually get, even if it isn't correct, you won't have to backmatch much until you do get to the correct answer. So I reckon you should be favoring the big buttons. And A-star does that. So I think this is an A-star problem, really. This yeah. So maybe we do that. So let's try it and see what kind of numbers we get. And it may well still take a long time, but I don't think it'll take as long as this recursive backtracking, whatever it is I did. I don't think this is really going to work. I did think of a different thing, which I thought was dynamic programming, but then I realized it would still be exponential time, which was to kind of like take the first K buttons out of these buttons, and you do some sort of dynamic programming where you try to solve with only the first K, and ultimately you're trying to solve with all of them, but you first solve the problem with the first K, and then add this in and solve it. Ultimately, I think whatever that was, it's still going to be exponential time because there's still like this many different states, different goals. This multiplied together. I don't see any way around that. I think this could also be an LP problem or an integer program. Ooh, hang on. What if we use... What was it? Z3? The thing that we used before in one of the previous problems? This could be an integer programming problem. Like, what are we trying to do? We're trying to choose... We're trying to minimize... So we're trying to choose... We're trying to choose a... Oh man. This... Okay, this is actually starting to look... like we can set it up as a Z3 and just have Python do it. We're choosing a vector of integers such that the dot product or the vector sum or whatever, I don't know the terminology, will equal, strictly equal that. What are we trying to minimize? We're trying to minimize the raw element-wise sum of that vector. That's completely an integer programming problem, isn't it? Okay, so I was about to code a star search. I feel like throwing it into Z3 might actually be better here. Let's see if I can remember how to do this. And then it will do whatever it does behind the scenes, like linear programming, relaxations to get approximations, and then rounding and all that clever stuff it does behind the scenes, which I used to know back in the day, but now you just let libraries do it for you. Yeah, okay, so we've got two potential approaches here. Let's try this. Z3. From, what was it? Z3 is, where's Z3 from? Install it, don't you? Install and import package Z3. Let's do that. So let's minimize this. This is just no good. Oh no, not this one. This one. Let's try new. Define get IP solution goal buttons. Okay. All right, Z3. I don't remember how to use Z3. Let's look up a tutorial or something. Alright, let's just have a look at some guides, remind myself. It'll probably come back to me. Once we look at this stuff. Oof, light mode. Z3 import star, yeah, let's do that. 3. Okay, so integer variables, so we want to create like basically constraints equals what is... Alright. Solver.add constraints. So can you just add them one by one? Let me just copy this in just to give me some assistance here, but I'm not using it. Alright, let's figure this out. So I want to... Okay, so we'll say x1 through to x something is the number of times we add each of these, right? So it would be... What? Okay. Say for k in range length of buttons, x how do we... Hello, MBZ. Welcome in. Learning how to make your own Wheel of Struggle submission. No, but wait, what? Wait, are you referencing something with that? Was there a submission I made before which looked like this? What we're actually doing is to describe this. Oh, are you learning how to make a game? Oh, make an actual game. Ah, okay. No. Well, at least I hope not. We would, if I was, this is not a game we would want to play. It's basically... Oh, it's kind of like those, you know, in puzzle games where you have a bunch of lights and there's like, you know, if one switch controls these lights, like maybe these 4 lights, and toggles them, and then another switch toggles some other set of lights, and you got to turn them all on. It's basically that, but on a massive scale and horrible, and not even can't really do it by hand. You need a computer to do it. But yeah, it's basically that. We have a set of like values we want to reach, and we have a set of buttons which increase. So this oops, that button there, the buttons in brackets, says that if we press this button, it will add 1 to light 0, light 1, light 2, light 3, and light 6. Or alternatively, if we were to press this button here, it will add 1 to light 4, 5, and light 6. And the goal is to find some combination of buttons that will make light 0 exactly 54, light 1 exactly 55, and so on. We have to hit exactly that target. So we've got to find an arrangement of buttons to press. But not only that, we've got to find the minimum number of button presses to do as well. To do that. And we've got to do it basically 200 times for all of those. And I'm having a lot of trouble doing this because the last solution I wrote earlier in the afternoon, I started running it and then I left it running for like 4 or 5 hours, and it reached as far as number 13, and I've got 199 to get through. So that wasn't fast enough. So yeah, that's what I'm trying to do. Yeah, it's not a game anyone would really want to play on the Wheel of Struggle, but it is a struggle. But now I'm realizing there is a sort of a library in Python, which some call it a bit cheaty, but I mean, the point of programming is to be lazy and to get code to do things for us. So I'm going to try and using that. It's called Z3. It's basically a clever, it's not like AI, it's deterministic, so it always does the same thing every time you run it, but it's sort of a smart system for solving equations similar to that. So if you just plug in, you just tell it what my constraints are, what my values are, what I want, and then let Z3 sort it out. Z3 will hopefully spit out an answer. That's what I'm trying to do now. And it means we don't have to care about what Z3 is doing behind the scenes. It's doing some complex algorithms, sometimes involving geometry, where it's trying to draw lines, find the crossing points, and find the optimal way of arranging things. But it's something we can just kind of give to Z3 and let Z3 figure out. That's what I'm trying to do now. So the language we have to use is we have to tell Z3 what our buttons are. Where did I write this? Here, okay. So we need to tell Z3 what the buttons are and what they do. Why did I write this here? Take that out. Alright, this code is all trash. We can just hide it because I don't think it's just too slow. Writing from scratch now. So for k in range, so for each of the buttons, from 0, 1, 2, 3, up to the number of buttons, I guess we want to create a thing called variables. We create a variable for the button. I mean, the nice thing about Z3 is it's not, you don't really need to know much programming to use it. You're mostly just kind of, you just need to know the barrier between how we describe things to Z3. But you don't really have to write much code other than that. So we're telling it, these are my variables. So I want to say variables.append. Ints. Let's just say X. Hello, Amaro. For a second, I thought you were still streaming since earlier. No, I ran my program. I left it running. I went out for lunch and then got distracted by things. And several hours later, I came back and it only got as far as problem 13. In fact, problem 14, I think it's just pretty much unsolvable with that recursive algorithm I had before. So I've scrapped that. I'm going to try using Z3 now. So I forgot all about Z3, but Z3 was something I discovered through Advent of Code a few years back, and it's kind of like the integer programming solver. I think it might be able to just do it. I left a brute force solution for part 2, and 9 hours later, it wasn't done, so I'm trying again. Yeah. Was your brute force using any kind of memorization or anything? Like, I turned off my memorization because I thought it would actually just slow things down. But maybe I was wrong. Maybe I should have left it on. But just delete the cache after each problem. I don't know. But I'm probably not going to stick with that approach anymore. Hello, Slinky. I'm on problem 10. Even though problems 8 and 9 are not done yet, I'm just trying to keep up with the current day before I... So I am falling behind, and tomorrow I'm going to have a huge backlog to try and fit in if we're actually going to finish on day 12, but I don't know if that's going to happen. 10 is an interesting problem. I'm trying to use Z3, so if this works, Z3 should just solve the problem for us. It's an integer program solver. Ints. Ints. It doesn't like ints. What's wrong with ints? Alright, I need to look up a up-to-date Z3 guide. I think that's just out of date. Z3 JavaScript? No. I want Z3 Python. Alright, here we go. Sorry for the blinding white mode documentation. It's int. I guess, do we need to give it a name? I'll give it a name anyway, I suppose. Could try 8 to at least get all the silver stars. Not tonight. It's like the evening for me now, and I just don't feel up to any programming. I think if I manage to get 10 done, I'm just going to go play San Andreas or something. Int. Z3, we've imported it, right? Z3. I don't think this is how we do it. Hang on. No, don't do it like this. Just say x equals int it doesn't recognize int, but I should have imported it. Z3. Let me have a look in the modules. Maybe it's not actually called Z3. Maybe it's Z3 solver or something. Or I just look up a previous Advent of Code where I actually used it. Wait. No, not plugins. What's it called? I don't remember how this works now. They've changed the layout of this. Project settings. Hang on. Wait. I can't even find a thing called project settings anymore. Where have they put all this stuff? Project settings. I'm right-clicking on the project. There's nothing called project settings anymore. Python packages. Okay. Boto pip Z3. Backup ZFS snapshots test 3. I don't think this is right. Uninstall that. I think it might be Z3 solver. Where's the market? How do I... Z3, is that just like something S3 related to the storing things? Right, how does this work? Search for packages. Okay, Z3 solver. There it is. That's it. Well, I'd prefer to use the whatever it's called, the built-in marketplace thing, just to make sure I'm getting the right one. Yeah, I could do that. All right. So okay. Variables.append int x. Just, I don't know, just just give it a name. So x1, x0, x1, 2, so on. All right. So we've created variables for the buttons. Now what? Constraints. So one constraint is that every x is greater or equal to 0. Constraints. For k. How do we add a constraint if we don't know the name of it? I've got a variable number of variables here. I don't know the names of those because it's like they're anonymous. But we do have pointers to them. How do I... All of this documentation is assuming we know the names of them. List comprehend. Oh, okay. Here we are. All right, let me go this. This might be a bit more useful. Okay, so yeah, we're doing something like that. Okay, fine. So my X is this, essentially, but... So X equals, let's say, int... Oh, God, that's an ancient way of doing it. Even dot format is not really used anymore, but I just like to use it. Int dot format k for k in range length of buttons. All right. So that's my x vector. We're trying to find the solution vector x. And we want the so for each of these buttons, we need to build a matrix, don't we? We need the first row. So there's going to be a binary matrix where each of these buttons is a... Why can't you treat this as binary? I already am. But the number of times you press each button is not binary. It's because you have to reach these targets, which are like unbounded integers. But each button is binary in the sense that it adds 1 to these specific counters. Oh yeah, I'm doing part 2. If you go to the website and you haven't solved it, you only see part 1, where it is actually binary. Yeah, that was an easy part. I've done that. If you solve part 1, you unlock part 2. So it's no longer the lights puzzle. Now it's more of a algebra puzzle. You're trying to sum these algebraic expressions to get that exactly that vector there. And each button adds 1 to each of those. The light status is actually relevant in this one, yeah. So this is an integer program, definitely, and I think Z3 will actually solve it. I'm trying to understand how to... Okay, so that's the x vector. Now we need to make a matrix, I suppose, where each row is going to be just zeros and ones, and it'll have length like this, and each button will contribute 1 row where it'll be a 0 or 1 depending on these numbers. Oh, don't move things around. Oops. 0 or 1. And goal... Wait, is this right? Yeah. And we want our constraint is that this matrix pre-multiplied by x, this vector x, equals the column vector, which is this goal. Yeah? Is that good algebra? I think so. And we also want x to be positive definite, which means it's all non-negative values. That's also a constraint. But those two things I've described are the most basic algebraic expressions in like linear algebra. So hopefully that's actually... All right. So what do we do? How do I make a matrix? So we don't need to use NumPy. Well, we could use NumPy, but we don't need to use NumPy. We can just use lists of lists. 3x3 matrix of integer. Okay. Or should I use NumPy? I think maybe I should just dig up the Advent of Code problem I did before, because I'm pretty sure I did something like this. Using Z3 with NumPy. Let's just carry on as I am. It might be fine. Using backtracking plus pruning now. Alright. Let's get rid of that. So the matrix, let's call it A equals empty list. And then for button in buttons row equals, it's going to be 0 for... Alright, let's just say n equals length of goal. That's the size of all our vectors. And like length of buttons is a different length. Button row equals 0 for range n for the w in button row w equals 1. So that's a binary row. Pop it onto the matrix. So we have a matrix. We have an X. Now, one constraint is... Okay, how do I... Maybe Z3 is overkill. This is actually... No. Z3 is probably... No, because it is integer. An integer problem. If it was a linear program, we would like have fractional values and stuff, which is not what we want. Z3 is the lazy way, yeah. That's what, yeah, that's good programming. Alright, so can I just say something like x greater or equal to 0? I don't think it does like vector stuff like this. What does it? I mean... Oh, there's actually an easier way to do this. We can do this. That just does what we're trying to do, but that's gonna be length of buttons. Equations. I'm just looking at a bunch of guides for different things. Oh man, maybe I should dig up that. What happened to a code problem? I think it was like a physics type problem. I mean, this might just be right as is. Maybe we just leave that. All right, x is greater or equal to 0. That's a constraint, but we need to put it into. Okay, so we've got S is solver. Okay, so we create a solver. And then we do s.add the constraint that x is positive definite. Okay, that's the easy one. Let's try running that, see if it breaks or anything. No, stop. No, it doesn't like that. Alright, how do I tell it that? This... sure someone solved it in 10 minutes with 5 lines in Python. Yeah, I wouldn't be surprised. X0. Alright, well, we know we can do it this way. We can just say... Okay, create the solver to begin with. And for k in range length buttons s.add x k greater or equals 0. Okay, fine. That is a constraint. And then, what about this matrix? Do I just have to write out the full matrix? Like, I don't think we can just tell it how to multiply matrices. We have to write out the row. So part 2 is just hitting the buttons with each wiring, adding 1 to the total output. Yeah, for each of those lights. Well, they're not lights anymore, but for each of those counters. Ooh. Oh, okay, we can use list comprehensions this way. We can do this instead. What? S.add x greater or equal to 0 for x in x. Okay, we can do that. Alright, don't worry about matrices, we can just do it row by row. So we can say, the button in buttons, row is that. Okay, so we've made the row, don't put it into a matrix. I'm sure there is a way, because I think I've done it before, but let's just say now we do the dot product between okay. So we want just sum of x row k times row k times xk equals goal sum of row k times xk equals goal k. Is that right? Equals. Yeah, but is Z3 gonna understand that? I don't know what Z3 does or doesn't understand. And no, that's wrong. Hang on. K in range n. So the dot product of row with x equals that element of the goal. And that's wrong. Hang on. No, it's not k. No. It's hang on. I gotta think this through. Oh, this does go inside there. No, it doesn't, does it? Hang on. Oh, no, we're not. Okay. If we look at each element of the goal from 0 to n-1, for that element, we're saying that for every button which which affects that particular counter, if you add up the number of times each of those buttons is pressed, it should equal that row, right? That element of the goal. How do I put that into words? So for button in buttons, okay, take that out. So it's like a linear equation, yeah, except it's an integer equation. That's the only reason I can't just plug it into an LP solver, which would actually be efficient. IP solvers do smart tricks to try and speed things up, even though they're technically exponential. But it is actually a linear equation. The only thing which is confusing me is the language of Z3, but like once you get the hang of it, it shouldn't actually be that bad. All right, so we've got we understand what the buttons are, and we've put them into a matrix or whatever. Let's just just put them in here. Okay, now for k in range, not buttons, let's just say I in range n. So that is for each goal element. So I'm going item by item here. I've got 44 here, and my constraint is that each element of X multiplied by the 0 or 1 value of whether it's included in that button, that dot product equals that number 44. That's what I'm trying to say. All right, okay, that makes things clear now. So I'm trying to say sum of, so it's X K times a so it'll be the kth row and the ith column. Is that right? And that's I. That's so confusing. I should be drawing a diagram of this, but okay, that looks, so AK is basically like the kth row of this. So it's for each button from each of these rows is a button. The ith column always corresponds to 0 or 1 for whether that particular counter is affected. And I is the counter we're interested in right now. So that counter is the column. And we're going through each of the rows, taking the 0 or 1 value and multiplying it by xk, summing all those values, and it should equal the goal. Could try this. Is that a valid constraint in Z3? I mean, it looks like it's all made up of primitives, so maybe, I don't know. So that is the constraint. That's it, right? Nothing more. It's actually a very simple, it's as simple as IPs get. Integer programs, like everything is greater or equal to 0, and everything sums to a particular value. That's what we're saying. Okay, the last thing we need to tell it is we want to minimize. Oh, for Z3 we need to have capital S here. Because we're using the Z3's understanding of sum. Okay, oh, how do we... Oh, and we're trying to minimize. What's the language for that? Solve. Solve. Also, we should be... It's not a solve. We're not trying to find a solution. It will work, but it won't find the minimal solution. We actually need to change it to optimize to do a minimizer. And then finally we need to do s.minimize. Is it sum of x? All right, and then we could just copy some of this code. If it's satisfiable, which it should always be, hopefully. Model equals s.model minimized x. Wait, what does this mean? So how do I get x out of it? Do that. No, we're not trying to minimize x. We want to model. What are we trying to do? Yeah, we're trying to get the value of x. Just say x. Let's just print it and see what happens. Z3 exception. All right, fine. Just what's in the model? Just tell me what you've got. It seems like it solved it, but print. Print model. Just what's in there? Model dot. Okay, just print the model. So those are the values. Those are the integer values. Okay. How do I extract those? What is that format? Model. For the k in model, print model. What, is this an iterable? gotta look at this documentation again. These guys don't really tell me what I want to know. How do I get the answer now? It's there, staring at me in the face. You index into the model. Okay, what's the index? Solve.model. Okay, fine. For K in... Oh, why was I printing model? That was the... God. Okay. Okay, okay. No, but I want to know the value. Okay. Okay, okay, do this. Model. There we go. There's the numbers. Have you tried optimized linprog from SciPy? But that's a linear program. So it will give you fractional values. Which, I mean, you can use that to, like with rounding, to try and find a close integer solution, but it will give you like 0.7 of this and 1.3 of this. It will use fractional button prices. I mean, there are special problems where it just so happens that the solution to the linear program might actually coincide with the integer program. I don't think that'll be the case here, though. I think the actual linear program solutions will probably be like fractional values. But it could work. I mean, there's a whole branch of science around using linear programs to estimate or get close to the true solution for integer programs. It's like a huge field of research, but I don't remember any of those methods. And that's actually what Z3 is already doing, essentially. It's just doing a lot of those clever patterns. Okay, we just return the sum of... Okay. Return... Okay, fine, just do return sum of model K for K and model. There we go. Let's try that then. No, what is it doing? It's still in Z3 language. How do I... I don't know, cast it to an int? Or get value or something? Model K dot as long. Okay, as long. Get it as a long int. Oh, that ran fast. 45, 68. How does this compare with our 45, 68, 46, 58, 92? 204. That's as far as we got with the... Oh my god. This could be it. That was instant. Oh my... This is exciting. I mean, it coincided with the values for that, so this better be right. And even if it's not, I think it'll only take a couple of tweaks to fix it if I've made a mistake somewhere. Yes! Z3. That's how you cheat with style. But that's what you do. Z3 is used in research and industry for a reason, because it's good stuff. And by all means, it's good to practice using it. That was so fast. And it's because it's such a regular looking integer program. That's like the quintessential integer program. It looks so much like a linear program, and it has the most basic constraints. Everything's positive definite. This matrix pre-multiplied by this vector, whatever, equals exactly this vector. That's as basic as it can get for the formulation. So, it knows all the tricks. And I used to know some of those tricks back when I studied nonlinear optimization, which was a tough course. Can you go over the code again? Yeah, okay, so so you want to see the Z3 related code or just everything else that is working outside it? And there's not really that much outside of it. So the Z3 code. So we've got our goal for what we want the counters to look like as a tuple. Z3 code, yeah. Okay, so the buttons comes in. So it comes in this form. The buttons are a set of tuples which just explicitly say the indices. And the goal is a tuple which looks like that exactly. So the Z3 language, we create this int vector, and it's basically the number that's pre-multiplied by each button, i.e. how many times we press each button. X is a vector that describes how many times we press each button, so it has length. We should have said m equals length of buttons, so it has length m essentially. And then in the Z3 language, we want to use an optimize. You can use solver. So if I wrote solve here, solver, could try that. Solver, and do solve. It will just find a x value which works, which may be what you want, but it's not going to find the best one. So it'll just be like solver dot s dot solver. No, it's not. It's s dot. Let me just look this up. I'm interested to see if it's s dot. No, you just say solve. Solve. No, wait. What is S? S is solver. I've got to look at this. Alright, doesn't matter. But you could write it as a solution, which will just find a solution, but let's just leave it the way it was. Unless it's you just change this word. Let's see what it comes up with. Dot. Dot solve for. Yeah, it's probably solve for. Oh, it doesn't. Okay, whatever. Doesn't matter. There is a way to do it. And in theory, it should be easier because it's not trying to find the best. So we've told it to use the optimizer. Then for each button, we want to specify that x is greater or equal to 0. So if we took this out, and we're allowing x to be negative, let's see what happens. Does it come up with better values? Yes, so it found a better solution, 55 than 68, where you're allowing negative presses, which could work if you're subtracting voltage, so you can remove that vector voltage instead of pressing it. So you have to add that constraint. So x is positive definite, and then I created for convenience, but I'm pretty sure there's a way you can just make A as a matrix, and then you just tell it. You just tell Z3 that I want this matrix multiplied by this vector equals this vector. Then we don't have to write all this long-winded stuff. We do have to create the matrix, but then we don't have to do this for loop. We just say there's one constraint, A times X equals M, or whatever. I just don't know, these guides are not clear because they've dumbed it down a lot. And it checks for satisfiability, i.e. whether it's possible, which it should always be according to the input. That line there is probably the most confusing, but it's really just tying every X to the corresponding button boolean, whether that button contributes or not. Adding up all the presses of each button, and that should equal the number of presses specified in the goal. That is done on a row-by-row basis. And then we tell Z3 we want to minimize that expression there. But there's a lot more you can, ways you can tell Z3 to do stuff. It's quite clever. You can tell it to, so there's a command called simplify, so you can tell it to simplify expressions. You can tell it to, what else? Or you can use real vectors, Boolean vectors. You can tell it to solve logical equations. Yeah, I'm looking at the advanced topics stuff here. There's all sorts of stuff you can do. Yeah, like basically before AI became something which could solve these problems just by pasting the problem in, which is now the case, Z3 was the most cutting edge way of solving problems the lazy way. And it's allowed. Eric's aware of Z3 and he's actually pretty happy people use it because it's different from AI because it's deterministic and it has a set formula and set tricks that it uses, so it's not hiding anything or it's not just finding solutions. It knows. It is following a process which is repeatable, so so it's all fair game. It's actually calculating, not doing probability guesses, yeah. Or I mean, yeah, well, okay, no, deterministic is probably, it probably is deterministic, but that is not a requirement. Like, it would be fine if it wasn't. I guess determinism doesn't matter. Like, there are algorithms where you use random numbers, like quicksort, for example, to get solutions. That's absolutely fine, I guess. I guess what I meant really is that the process is not obscured. Like AI, you've no idea what it's doing. It probably just found a solution that someone did before and is working off that. So yeah, some of these problems, Z3 is pretty good. The last time I did it, I can't remember when it was, but it was like for a physics problem with lots of asteroids moving about. You had all these equations for the speed and the velocity and the positions of the asteroids, and you had to find where they all collided or something like that. And it was quite hard to like from first principles, but Z3 became a bit of a meme. A lot of people just used Z3 for that. Can't think of a fast way to do this in GML. I have to write Z3 myself. So because this is a very regular looking LP, it probably uses a standard LP relaxation technique, which is not too difficult. So you could try running it through an LP, see what you get, and it could be the case that you just have to round it to the nearest integers or something like that, and it might actually be the right answer. I wouldn't be surprised. LP rounding is a valid way of solving problems sometimes. I think because it's so regular looking, and there's probably some pretty basic algorithm it's using. I don't know. I was gonna write A star for this, and then I remembered Z3. I think A star is probably better than like any recursive backtracking technique, because A star is, the idea would be that I would prioritize going for the big buttons, which I think is what Z3 is doing anyway. It's probably prioritizing the big buttons. And when you hit a dead end, start trying the smaller buttons. Alright. Well, I don't feel like doing 8 or 9 today, so I might have a lot to do tomorrow. Have a look to see if anyone's actually still streaming App End of Code. I mean, yeah, there might be. Some people just started now, I guess, if they're around the world. Bad Cop is still live? Has he been live since the problem released? I think he has. He's been on for hours. Let's have a look. Yes, wow, okay. Bad Cop is doing pretty cool streams because he's always trying to solve it in Bash, which is horrific, and I don't recommend anyone do that, but he does it so you don't have to. Wait, is he actually doing it, or is he doing something else now?
Solve for each tree individually.
He's doing something with ChatGPT. I don't think. Maybe he's finished the problem and just doing other stuff.
For a squirrel, you don't care which tree gave you the acorns.
But yeah, Bash, and he succeeds. I think he's solved every problem to date with Bash, which is absolutely crazy. This person is doing problem 9, which was what I was doing yesterday. All right, let's rate them. And I'll have to finish 9 tomorrow or whenever. All right, and after I take a short break, I'm going to come back with some San Andreas to cool down, blow up some helicopters, eat some oysters. Yeah, Imara, I guess that's one way to do it. I mean, it looked like my brute force was working, and then it got stuck on on line 14 or something, and just I don't think it would ever get past that. All right, thanks for watching. That in the end, that was actually a pretty good problem. I like that. I'll have to see what non Z3 solutions are. I have a feeling A star would work as well. Just it wouldn't be fast. It would probably take like 10-20 minutes or something. All right. See you next time.